Hello, in this lecture we'll prove Stewart's theorem using two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CBN. Here we have triangle ABC. The length of side AB is C, the length of side AC is B, and the length of side BC is A. And also note that the length of line segment BD is M units, and the length of line segment DC is N units, and the CBN in this triangle ABC, is line segment AD. And the length of this CBN is D units. Okay? So, I repeat again, Stewart's theorem yields a relation between the lengths of the sides of the triangle, those two sides, to the length of the CBN AD that is equal to 2 units. And according to Stewart's theorem, B square M plus C square N equals to A, and in the brackets we have D square, the length of the CBN square, plus M times N. Okay, so we have a relationship between the lengths of the sides in the triangle and the length of the CBN AD. Okay, so we'll prove Stewart's theorem according to the first method. We will do a construction, that is to say, from the vertex A of triangle ABC, we draw perpendicular on side BC. Okay. So this angle equals to 90 degrees, and this angle also equals to 90 degrees. According to our construction, we will define the touching point of the perpendicular from point A and BC as E. We will define line segment ED, this line segment as X. That is to say, line segment ED equals to X units in its length, according to our definition. We will define line segment AE as H. What is the length of line segment VE? The length of this line segment VE. From doing it is very easy to see that BE equals to BD minus ED. Okay, BE equals to BD minus ED. I write it down. BE, the length of line segment BE, equals to BD minus ED. So BE equals to BD equals to M units in its length, as you can see here, and ED equals to X according to our definition. So we substitute BD by M and BC by X, and we get a conclusion that BE equals to M minus X units in its length. Here, line segment BE equals to M minus X units. Likewise, the length of line segment EC, although it is very easy to see that EC equals to X plus N. So I write it down here that EC, this line segment EC, equals to X plus N units. Hold on, that EC equals to X plus N units. In the next step, we'll implement the Pythagoras theorem on the right triangle AED. Repeat again, we'll implement the Pythagoras theorem on this right green triangle, triangle AED. By PT is abbreviation for Pythagoras theorem. Actually, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right green triangle, triangle AED, the hypotenuse is AD, therefore the square of the hypotenuse is AD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE squared plus AD squared. Okay, AE squared plus AD squared. Repeat again, according to the Pythagoras theorem, in the right green triangle AED, we found out that AD squared equals to AE squared plus AD squared. Okay. AD equals to D units, therefore AD squared equals to D squared. And equals to AE squared. AE equals to H, therefore A squared is H squared plus ED squared. ED equals to X, therefore ED squared equals to X squared. In conclusion, I found out that according to the Pythagoras theorem, D squared equals to H squared plus X squared. In the next step, we'll implement the Pythagoras theorem on the right triangle AEC. On the right triangle AEC, according to the Pythagoras theorem, in the right triangle AEC, AC squared equals to AE squared plus EC squared. Repeat again. In the right triangle AEC, according to the Pythagoras theorem, AC squared equals to AE squared plus EC squared. Okay. So this will be equation number 1. AC equals to the unit is length, therefore AC squared is C squared, that is equal to AE squared. AE equals to H, unit is length, therefore AE squared is H squared, plus EC squared. EC equals to X plus N, unit is length, therefore EC squared is X plus N squared. In conclusion, I found out that according to equation number 1, in the right triangle AEC, C squared equals to H squared plus X plus N squared. Here we'll open the brackets on this side of equation number 1, and we'll get that according to equation number 1, C squared equals to H squared plus x plus n squared equals to x squared plus n squared plus 2 times xn. In this equation number 1, we have h squared plus x squared, and we have already found out that h squared plus x squared equals to d squared. So we substitute h squared plus x squared in this equation number 1, by d squared. So we do it now and we get that c squared equals to h squared plus x squared is d squared plus n squared plus 2 times xn. Okay? According to equation number 1, c squared equals to d squared plus n squared plus 2 times xn. In the next step, we will implement the Pythagoras theorem in the pink triangle. Triangle AEB. I remind you again that by PT is a relation for Pythagoras theorem. So, according to the Pythagoras theorem, in the pink right triangle AB, AB square, that is the square of the hypotenuse, must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE square plus EB square. I'll repeat again. In the pink right triangle AB, AB square equals to AE square plus EB square. Okay. This is equation number 2. So AB equals to C units in itself, therefore AB square equals to C square. This is equal to AE square. AE equals to H, therefore AE square equals to H square plus EB square. EB equals to M minus X, therefore EB square equals to M minus X squared. In conclusion, we found out that according to equation number 2, C square equals to H square plus M minus X squared. We will open the brackets in this side of equation number 2, and we will get that according to equation number 2, C square equals to H square plus M minus X square, according to the algebraic identity that A minus B square equals to A square plus B square minus 2 times AB, we get that M minus X square equals to M square plus X square minus 2 times MX. Again, we have here in this equation number 2, AH square plus X square x squared plus x squared equals to this squared. So we substitute x squared plus x squared in this equation number 2, by this squared. We do it now and we get that c squared equals to a squared plus x squared is this squared plus m squared minus 2mx. This is equation number 2. And we have already found out that according to equation number according to equation number 1, in equation number 1, we implemented the Pythagoras theorem on triangle AEC. This triangle AC. So according to the Pythagoras theorem, AC squared equals to AE squared plus EC squared. So AC is B. Therefore, AC squared is B squared. Yeah. AC squared is B squared. AC squared is B squared. Okay. So according to equation number 1, we have already found out that B squared equals to D squared plus N squared plus 2 times Xn. Okay. In the next step, we will create equation number 3 by equation number 3 will be created. It will be equal to the multiplication of equation number 1 by m, then we will multiply equation number 2 by n, and then we will add the two equations together. This will yield equation number 3. Okay, so we'll do it in 2 steps. First of all, we will multiply the right side of equation number 1, this right side of equation number 1 by m. Then we will multiply the right side of equation number 2, this is the right side of equation number 2 by n, and then we will add the two equations together, and that must be equal to the multiplication of the left side. This is the left side of equation number 1 by m plus the multiplication of this equation number 2 by n. Okay. So first of all, we will multiply the right side of equation number 1 by m. This is the right side of equation number 1. So inside the brackets we have d squared plus n squared minus 2 times xn plus the multiplication of the right side of equation number 2 by n. So it is n. This is the right side of equation number 2. So inside the brackets we have d squared plus m squared minus 2mx. Okay. And it must be equal to the multiplication of the left side of equation number 1 by m. In the left side we have b squared only, so it is m times b squared plus the multiplication of the left side of equation number 2 by n. In the left side of equation number 2 we have c squared, so it is n c squared. Okay. So in the next step, we'll open the brackets on this side of equation number 3. And we'll get here that according to equation number 3, we have m times d squared is md squared, plus m times n squared is mn squared, plus m times minus 2xn is minus 2xmn, plus n, so we'll open the bracket here also, n times d squared is nd squared, plus n times m squared is nm squared, plus n times, so here we have here in the right side of equation number 1 we have d squared plus n squared plus 2xn, and therefore m times 2xn equals to plus 2xmn. So here it is plus 2xn, and therefore m times 2xn equals to plus 2xmn. And here we have n times minus 2mx equals to minus 2mxn. And the right side equals to the left side. So in the left side we have mb squared plus nc squared. Okay. So this is actually equation number 3 after we open the brackets. Here we have 2xmn minus 2xmn is 0. So those two expressions will get cancelled. In the next step, we'll take out a common factor from mn. We'll take out the common factor of d squared from md squared and also from nd squared. Okay, md squared, after we took from it d squared, a common factor, inside the brackets we have m, plus after we took d squared as a common factor from nd squared, inside the brackets we left with n, plus we'll take out a common factor of m times n from mn squared and also from nm squared. So what is left from nm squared after we took from it mn as a common factor? What is left is actually m. And what is left from mn squared after we took from it mn as a common factor? What is left is n. And we also here, so it is equal to mb squared plus nc squared. In the next step, we'll take out m plus n as a common factor from those two expressions. So m plus n is taken as a common factor inside. So what is left from this equation after we took from it m plus n as a common factor? What is left is actually d squared. What is left from this expression after we took from it m plus n as a common factor? What is left is actually mn, which is plus mn, and is equals to mb squared plus nc squared. m plus n equals to a. Here I'll show you from the domain. Here BC equals to BD plus DC. Again, BC equals to BD plus DC. That is to say, BC equals to BD that is M plus DC that is N. So BC equals to M plus N from one side, but from the other side, according to our definition, BC equals to A also. Therefore, M plus N equals to A. M plus N equals to A. So we substitute M plus N in this equation number 3 by A. And we have here M plus N is A, and inside the brackets we have D squared plus M times N equals to B squared M plus C squared N. And this is actually Stewart's equation. We proved that Stewart's equation is true. So we finished the first method. In the next step, we prove that Stewart's equation is true according to a second method. So I write down again Stewart's equation here. According to Stewart's equation, B squared M plus C squared N equals to A. Inside the brackets we have D squared plus MN. Okay, so we prove that this equation is true. Okay, so the first step, we define angle ADB, this angle is theta. We know that BC is a straight line, and we know that the sum of the angles on one side of a straight line must be equal to 180 degrees. So if you focus on the upper side of the straight line BC at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1 that I mentioned. Therefore, the missing angle must be equal to 180 degrees minus theta. You can see here that 180 degrees minus theta plus theta equals to 180 degrees, exactly according to rule number 1. Okay, in the first step, we'll implement the law of cosines on the green triangle ACD, and then we'll implement the same law in the pink triangle ADC. I remind you quickly what is the law of cosines. Actually, the law of cosines is true in any triangle. So this triangle ABC, could be any triangle. This is the law of cosines. This is triangle ABC. It could be any triangle. We know that the length of side AB of triangle ABC equals to A. The length of side AC equals to B units in its length, and finally side BC equals to C units in its length. And we also know that this angle BAC equals to theta. Then, according to the law of cosines, in this triangle ABC, we will get that the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. if we add to this equation c square equals to a square plus b square minus 2 times ab cosine theta. So if we add to this equation 2 times ab cosine theta and then we subtract c square and then we will divide this equation by 2 times ab, we will get that cosine theta equals to a square plus b square minus c square over 2 times ab. And this equation is true in any triangle. So we will substitute, we will implement this law, the law of cosines, in the green triangle ABD. Okay, so according to the law of cosines in the green triangle ABD, according to the law of cosines, we get that cosine theta equals to m square plus d square minus c square over 2 times md. So this equation number 1 is the implementation of the law of cosines in the green triangle ABD. Cosine theta equals to m square plus d square minus c square over 2 times md. In the next step, we'll implement the same law, the law of cosines, in the pink triangle ADC. This will be equation number 2. So according to the law of cosines, the pink triangle ADC, cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times dn. Hit again. This equation number 2 is the implementation of the law of cosines in the pink triangle ADC. Cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times dn. Okay, we have the trigonometric identity that cosine 180 degrees minus theta equals to cosine theta equals to minus cosine theta. I repeat again, cosine 180 degrees minus theta equals to minus cosine theta. So according to this trigonometric identity, we substitute cosine 180 degrees minus theta in this equation number 2 by minus cosine theta. And we'll get that according to equation number 2, minus cosine theta equals to d squared plus n squared minus b squared over 2 times dn. In the next step, we will multiply this equation number 1 by minus 1. So in this step of the equation, cosine theta times minus 1 is minus cosine theta. On the other side of the equation, we also multiply the other side of the equation by minus 1, of course. So it will be minus, inside the brackets we will have m squared plus d squared minus c squared over 2 times md. So we actually have here two different expressions for minus cosine theta. Equation number 1 and equation number 2. In the next step we will create equation number 3 that states that cosine minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Okay, so according to equation number 3 we'll get that minus cosine theta according to equation number 1 is minus m squared plus d squared minus c squared over 2 times md, and it must be equal to minus cosine theta according to equation number 2. And minus cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times dn. In the next step we will multiply this equation number 3 by 2d, and we will get that according to equation number 3, so we multiply this side of the equation number 3 by 2d, so we have, in the numerator we have minus 2d, 2d over 2d is 1, so 2d will get cancelled, and we left only with m in the denominator. The numerator didn't change. So in this side of equation number 3 we have minus m squared plus d squared minus c squared over m, and it is equal to, we multiply this side of equation number 3 by 2d. Here 2d over 2d is 1, so 2d will get cancelled, and in the denominator we left only with n. The numerator didn't change. Okay, in the numerator we have d squared plus n squared minus b squared. So in conclusion, we found out that according to equation number 3, minus m squared plus d squared minus c squared over m equals to d squared plus n squared minus b squared over n. Here we will cross multiply this equation number 3, and we'll get that according to equation number 3, minus m, inside the brackets we have m squared plus d squared minus c squared, and it is equal to m, inside the brackets we have d squared plus n squared minus b squared. Okay. In the next step, we'll open the brackets on both sides of this equation, equation number 3, and we'll get that according to equation number 3, minus n times m is minus nm squared. Minus n times m squared equals to minus nm squared. Minus m times d squared is minus nd squared. And finally, minus n times minus c equals to plus nc squared, because minus times minus is plus. So minus n times minus c squared equals to plus nc squared. And it is equal to m times d squared, m is md squared. M times n squared is mn squared. And finally, m times minus b squared equals to minus mb squared. In the next step, we add to this equation, equation number 3, nd squared, nm squared, nm squared. So nm squared minus nm squared is 0, and then we will add also nd squared. So nd squared minus nd squared is 0. And finally, we will subtract nc squared. Of course, from both sides, minus nc squared minus nc squared is 0. So, in this side of the equation, we left with 0. 0 equals, in the other side of the equation, we have already have md squared plus mn squared minus mb squared, and we have to add it to this side of the equation nm squared, so it is plus nm squared, and we have also to add nd squared, so it is plus nd squared, and finally we have to subtract also nc squared, so it is minus nc squared. Okay. In the next step, we will take out a common factor of d squared from md squared and also from nd squared. Okay, so what is left from md squared after we took from it d squared as a common factor? What is left is m. And what is left from nd squared after we took from it d squared as a common factor? What is left is actually n. And we also take a common factor of m times n from mn squared and also from nm squared. So what is left from nm squared after we took from it mn as a common factor? What is left is actually m. And what is left from nm squared after we took from it mn as a common factor? What is left is actually n. Okay? And it is minus mb squared minus nc squared equals to 0. In the next step, we will add to this equation, equation number 3, mb squared and also nc squared. Okay, plus nc squared. And we will get that in this side of the equation we have 0. So 0 plus mb squared is mb squared. And 0 plus nc squared is nc squared. And in this side of the equation we have d squared times m plus n plus mn times m plus n. Okay. In the next step, we take out m plus n as a common factor from those two expressions, and we will get that mb squared plus nc squared equals to, so we took m plus n as a common factor from this square m plus n times m plus n. So inside the brackets we left only with this square, and we took m plus n from a common factor from mn times m plus n. So inside the brackets we left only with mn. So actually, according to we already found out that in the first method that m plus n equals to a. Yeah, m plus n equals to a. So I'll not repeat on it. So we substitute m plus n in this equation number 3, by a, and we'll get that according to equation number 3, b square m plus c square n equals to a. Inside the brackets we have d square plus m times n. It again, we actually found out that b square m plus c square n equals to a. Inside the brackets we have d square plus mn, and this is exactly the equation of Stewart's theorem. So it succeeded to prove in both methods that this equation, that is the equation of Stewart's theorem, is true. In the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths sides of the triangle to the length of its CVN. Here, the length of side AB is C, the length of side AC is B, and the length of side BC is A. So we have here triangle ABC with the length of its sides, and the CVN in this triangle ABC is AD, and the length of the CVN AD is D. So, I'll repeat again, Stewart's theorem yields a relation between the lengths of the sides in a triangle to the length of its CVN. The CVN here is AD. Okay, and according to Stewart's theorem, b squared times m plus c squared times n equals to a, and inside the brackets we have d squared plus m times n. Of course, that BD, line segment BD equals to m units in its length, and line segment DC equals to n units in its length. So we actually have to prove that Stewart's theorem is true, that this equation is true. So in the first method, we did a construction. This is to say, from point A, we drew perpendicular on BC. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. We also defined line segment ED as X, and we defined line segment AE as H. What is the length of line segment BE? From the drawing it is very easy to see that BE equals to BD minus ED. BE equals to BD minus ED. BD is M and ED is X. Therefore, we conclude BE equals to M minus X. And here also, it is very easy to see that EC equals to X plus N. Line segment EC equals to X plus N. Then we implemented Pythagoras theorem on the green triangle, triangle AD. So the green triangle AD, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle AD, repeat again, that AD square equals to AE square plus ED square. Again, AD square equals to AE square plus ED square. Okay, here also AD square equals to AE square plus ED square. AD equals to D, therefore AD square is D square. AE equals to H, therefore A square equals to H square plus ED square. ED equals to X, therefore ED square equals to X square. So in conclusion, we found out that in the right triangle AD, D square equals to H square plus X square. Then we implemented the Pythagoras theorem on triangle AC. According to the Pythagoras theorem, on the right triangle AC, AC square equals to AC square equals to AE square plus EC square. I repeat again, AC square equals to AE square plus EC square. I repeat again, in triangle AC square equals to AE square plus EC square. AC equals to B. Therefore, AC square is B square. B square, and it is equals to AE square. AE is H, therefore AE square is H square. AE square is H square plus EC square. EC equals to X plus N, therefore EC square equals to X plus N square. EC square equals to X plus N square. In the next step, we open the brackets on this side of equation number 1. This equation number 1, and found out that B square equals to H square plus X plus N square equals to X square plus N square plus 2 times Xn. Okay? We have already found out that H square plus X square equals to D square. So we can substitute H square plus X square in this equation number 1, by D square. We did it here and we found out that B square equals to H square plus X square is D square plus N square plus 2 times Xn. So we found out that according to the equation number 1, B square equals to D square plus N square plus 2 times Xn. Then we implemented the Pythagoras theorem on the pink right triangle AB. On the pink right triangle AB, according to the Pythagoras theorem, in the right triangle AB. So according to the Pythagoras theorem, AB square equals to AE square plus EB square. Again, AB square equals to AE square plus EB square. I repeat again, in the pink triangle AB square equals to AE square plus EB square. AB equals to C, therefore AB square is C square. AB square is C square. AE equals to H, therefore AE square is H square. And finally, EB equals to M minus X, therefore EB square equals to A minus X square. In conclusion, found out that according to equation number 2, C square equals to H square plus M minus X square. Here we open the brackets on this side of equation number 2 and found out that C square equals to H square and A minus X square equals, according to the algebraic identity, that A minus B square equals to H square plus B square minus 2 times AB, we get that M minus X square equals to M square plus X square minus 2 times MX. Again, we have here H square plus X square that is equals to D square according to this equation. So we can substitute H square plus X square by D square. We did it and here and found out that C square equals to D square plus M square plus minus 2 times MX. This is equation number 2, and we have already found out that according to equation number 1, B square equals to D square plus N square plus 2 times Xn. In the next step, we created equation number 3. equation number 3 was created according by actually multiplying equation number 1 by m, then we multiplied the equation number 2 by n, and then we added the two equations with each other, and this created equation number 3. Okay, so we'll do it in 2 steps. First of all, we will multiply the right side of equation number 1. This is the right side by m. Then we multiply the right side of equation number 2 by n. This is the right side. And then we will add the two equations with each other, and it must be equal to the multiplication of the left side of equation number 1 by m plus the multiplication of the left side of equation number 2 by n. Okay? So here we have equation number 3, m times the right side of equation number 1. Here we have d squared plus n squared plus 2xn. So it is m times d squared plus n squared plus 2 times xn plus the multiplication of the right side of equation number 2 by n. This is the left side. So inside the brackets we have d squared. So it is m times d squared plus m squared minus 2 times mx. And it must be equal to the multiplication of the left side of equation number 1 by m. In the left side we have b squared. So it is m times b squared plus the multiplication of the left side of equation number 2 by n. In the left side we have of equation number 2 we have n, we have c squared. So it is nc squared. Okay. Then we open the brackets here. It is m times d squared is md squared, m times n squared is mn squared, and n times plus 2xn is 2 times mxn, and plus n times d squared is nd squared, n times m squared is nm squared, and finally n times minus 2mx is minus 2 mxn. Okay, this is the equation that was created, equation number 3, after we opened the brackets. Okay, so here we have plus 2xmn minus 2 mxn equals to 0. Then we took out d squared as a common factor from md squared and also from nd squared. So inside the brackets we left with m plus n. Then we took nm or mn as a common factor for mn squared and also from nm squared. So inside the brackets what is left is m plus n. And it is equals to mb squared plus nc squared. mb squared plus nc squared. In the next step, we took out a common factor from those two expressions, a common factor of m plus n from those two expressions. So here inside the brackets, we left with d squared plus mn, that is equal to mb squared plus nc squared. I show you here it again that it is very easy to see from the drawing. BC equals to A according to our definition, but BC also equals to BD plus DC. So BC equals to BD, that is M, plus DC, that is N. So from one side BC equals to M plus N, from the other side it is equals to N, therefore A equals to M plus N. So we can substitute n plus n by a. We did it here and we found out that here n plus n is a. Inside the brackets we have d squared plus mn, and it is equal to b squared m plus c squared. And this is exactly Stewart's theorem. In the next step we proved Stewart's theorem according to the second method. In the second method, we defined In the second method, we defined angle ADB, this angle is theta. And because of the fact that BC is a straight line, and we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on the upper side of the straight line BC at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1 that I mentioned. So which angles we have at the upper side of BC at point D? We have angle theta plus the missing angle. In total, they must be equal to 180 degrees. So this angle, the missing angle, must be equal to 180 degrees minus theta. Why? Because 180 degrees minus theta plus theta equals to 180 degrees. That is the sum of the angles on one side of a straight line. Exactly according to rule number 1. Then we implemented the law of cosines in the green triangle ABD. And then we implemented also the same law on the pink triangle ADC. So what is the law of cosines? The law of cosines is true in any triangle. So this triangle ABC could be any triangle. The length of side AB is A units, side AC equals to B units in strength, and side BC equals to C units in strength. And we also know that this angle BAC equals to theta. According to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times AB times cosine theta. After a couple of operations, it's very easy to see, on this equation it is very easy to see that we will get that cosine theta equals to A squared plus B squared minus C squared over 2 times AB. Okay, so this equation is true in any triangle, so we implemented the law of cosines in the green triangle. Triangle BAD. So in the green triangle, triangle BAD, according to the law of cosines, we will get that cosine theta equals to D squared plus M squared minus C squared over 2 times MD. Repeat again, in the green triangle ABD, cosine theta equals to M squared plus D squared minus C squared over 2 times M times D. Likewise, we implemented the same law, the law of cosines, in the pink triangle ADC. Here, according to the law of cosines, cosine 180 degrees minus theta equals to D squared plus N squared minus B squared over 2 times D times N. Repeat again, according to the law of cosines in the pink triangle, triangle ADC, cosine 180 degrees minus theta equals to D squared plus N squared minus B squared over 2 times Dn. We have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta, so we used this trigonometric identity and we substituted cosine 180 degrees minus theta by minus cosine theta in this equation number 2. And we got that here we have, it is minus cosine theta, and it must be equal to D squared plus N squared minus B squared. In the next step, we multiply this equation number 1 by minus 1. Cosine theta times minus 1 equals to minus cosine theta. And there we have minus, and inside the brackets we have M squared plus D squared minus C squared over 2 times MD. In the next step, we get the equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. So minus cosine theta according to equation number 1 equals to minus M squared plus D squared minus C squared over 2 times MD. And it must be equal to minus cosine theta according to equation number 2. And minus cosine theta according to equation number 2 equals to D squared plus N squared minus B squared over 2 times Dn. In the next step, we multiplied this equation number 3 by 2D. So here 2D over 2D is 1, so 2D will get cancelled, and we're left with, in the denominator, only with M. The numerator didn't change. Then we multiplied also this side of the equation by 2d. So 2d over 2d is 1. So in the denominator we left only with n, and the numerator didn't change. So in conclusion, we found out that minus m squared plus d squared minus c squared equals to d squared plus n squared minus b squared over n. Then we cross multiply these two equations, and we got that minus n inside the brackets we have m squared plus d squared minus c squared equals to m inside the brackets we have d squared plus n squared minus b squared. Then we open the brackets on this side of this equation. Here we have minus n times n m squared is minus n m squared, minus m times d squared is minus n d squared, and finally minus n times minus c squared equals to n c squared. We open the brackets also on this side of the equation. So m times d squared is m d squared, and m times n squared is m n squared, and finally m times minus d squared equals to minus m d squared. In the next step, we added to this equation mn squared. So here mn squared minus mn squared is 0, and we added also to this equation nd squared. So nd squared minus nd squared is also 0, and finally we subtracted from this equation nc squared. So nc squared minus nc squared is 0. So in this side of the equation we are left with nothing, is 0. In the other side of the equation we have already here md squared plus mn squared minus mb squared, and we have to add to this equation nm squared, and we have to add also nd squared, and we have to subtract nc squared. So this is the expressions that we got. And then we took this square as a common factor. We took out this square as a common factor from md square and also from nm square. So inside the brackets we left only with m plus n. Then we took mn as a common factor from mn square and also from nm square and also from mn square. So inside the brackets we left only with m plus n, and it is equal to minus mb square minus nc square equals to 0. So we added to this equation number 3, mb square plus nc square, and therefore we found out that mb square plus nc square equals to d times m plus n times n plus n. Then we took out m plus n as a common factor from those two expressions. So inside the brackets we left only with d squared plus m times n. In conclusion, we found out that according to equation number 3, mb squared plus nc squared equals to m plus n. Inside the brackets we have d squared plus m times n. We have already found out in the first method that m plus n equals to a, so we can substitute m plus n by a. We did it, and we found out that again m plus n equals to a. We substitute m plus n by a. So we have here m plus n, that is a, so it is a times d squared plus mn, and it must be equal to bm squared plus nc squared. This is exactly Stewart's theorem. Okay, so we succeeded to prove Stewart's theorem in two different methods. Okay, thank you very much.